What is your current position and what are your goals in getting a PhD in mathematics?
Hi, my name is Simon. I'm an associate researcher in computational neuroscience at the School of Medicine at Mount Sinai. So I've been working in computational neuroscience for a couple of years now, and I really like my research. I've sort of come to realize that a lot of problems in neuroscience are not mathematically well posed, and it has galvanized a desire to go back and do a PhD in math and sort of work on problems that are a little bit more well posed. My goal for getting a PhD, I'd like to embark on a career as a research mathematician working on problems in dynamical systems, probability, stochastic processes, and computability.
Why have you chosen Courant?
Courant has world-renowned faculty in dynamics, stochastic processes, probability, and mathematical neuroscience. Also, Center for Neuroscience is great, has a lot of really good researchers, and I would love the opportunity to collaborate with them and continue doing data analysis.
Who do you want to work with at Courant?
At Courant, I really want to work with Lai-Sang Young and Adi Rangan. So I met with them this past semester, and I found we have a shared interest in understanding the computational role of spike synchrony in cortical networks. So they've both written about this topic. And I think mathematically, I think it would involve sort of problems posed by high-dimensional stochastic dynamical systems, which Professor Young has done like a lot of work on, and I think there's a lot more work to be done, and I would like to do some of that work or help or collaborate. And I think Professor Rangan's work on higher-order correlations in the neural system as providing additional coding dimensions is very interesting and is sort of similar to my previous research, and I would like to work on topics along that line as well.
Why do you think you're a good match for Courant?
So I bring a lot of research experience in computational neuroscience. I've spent time staying close to neural data and spiking data and like building collaborations with prominent neuroscientists. I also have extensive computational skills, so I've done a lot of statistical programming in MATLAB and Python in my current job. I train neural networks in Python and PyTorch to solve motor tasks. And I also have extensive graduate coursework in mathematics, so I'm familiar with measure theoretic probability, dynamical systems, stochastic processes. So transitioning to the PhD program, I think, would be pretty seamless. So yeah, thanks for watching this video, and now I'm going to talk about some math that I really like. In this part of the video, I'm going to talk about how stochastic point processes can be used to model the activity of spiking neurons. So first, we consider an ensemble of M interacting neurons receiving some exogenous input x of t. And we want to write down a satisfying mathematical description of the set of spike trains generated from this population. The simplest way to do this is just to write down the set of spike times for each of the M neurons, and then define a counting process, and also let NMT denote the corresponding sample path, which is just a number of spikes in some window from 0 to t. Common models in this process, point process framework, include the homogeneous Poisson process, where the probability of spiking is given by some constant parameter. Spiking is famously very dynamic and non-stationary, and thus using a stochastic intensity function of time would make more sense. But spike trains also have these peculiar statistical features, such as refractory periods, bursting, correlations with other cells. And so we want to include these effects in our model. And so one way to do this is to use a conditional intensity function, which should give the probability of spiking given auto and ensemble histories and on conditioning on the input as well. And a natural model to serve as this intensity function is a nonlinear Hawkes process, where phi is some nonlinear function, mu is background spiking rate, you have temporal kernels that can model excitatory and inhibitory effects, and you have some filter applied to exogenous input. I think this model is really exciting because it can appropriately model the history effects in spiking while also being very close to the forefront of stochastic processes theory, the theory of stochastic processes. So I'm very interested in working on these topics during my PhD, and thanks for watching my video. Bye-bye.